Good day, everyone. My name is Sylvain Chatel, and today I'll be presenting our systematization of knowledge on privacy preserving collaborative tree-based model learning. This is joint work with Apostolos Piergelis, Juan Ramon Troncoso Pastoriza, and Jean-Pierre Hubot from EPFL. Machine learning has become prevalent in the last couple of decades, making data one of the most prized commodities. Among the plethora of machine learning algorithms, tree-based models have received a lot of attention in research and industry for several reasons. They are highly interpretable, they require little effort in data preparation, and can cope with nonlinear relationships. Finally, they can also be used for fast prototyping, and for instance, they can be employed in medical research to do quick proof of concepts of an experiment before training more complex models. Recent years have seen the new trend of collaborative learning. It refers to the setting where multiple entities wish to train on their joint dataset to obtain a larger dataset with higher diversity, which can in turn result in higher accuracy. Additionally, as data is quite valuable, there is a crucial need for data protection. Indeed, the training process needs to respect the data privacy, first to abide to new data protection regulations, but also to incentivize the collaborative learning. Model privacy is also instrumental, as first, the model could be proprietary, and second, the resulting model could potentially be used to infer information about the training data. As you can see on the right-hand side, the volume of publication on the topic of privacy-preserving collaborative tree-based model learning has been booming in the last couple of years. Thus, we propose a systematization of the literature on this topic and identify 4 dimensions piloting the constructions, which are the learning algorithm, the collaborative model, the threat model, and the protection mechanism. We also identify that even with protection mechanism, some information are still shared during the learning, resulting in potential information leakage. Thus, we also provide a leakage analysis framework to systematize literature with respect to this dimension. Finally, we identify some open challenges and future directions. So let us first look into the learning algorithms. As a quick recap, decision trees are supervised learning techniques that can be used for regressions or classifications. While the former can be used to predict continuous values, the latter can be used to predict or classify discrete values. Trees are often represented as direct acyclic graph, as you can see on the right-hand side. You basically have the data that has come from the path that is split with respect to a specific feature and a specific value. The initial algorithms that were introduced were called greedy algorithms, and for each node, the splitting feature is selected by evaluating a cost function, which is often nonlinear, evaluating an information gain or the Gini index, for instance, for all the features and all the possible split points. And eventually, the best gain is selected as the feature and the split. More recently, random algorithms were introduced to alleviate some issues of overfitting with greedy algorithms. The split is either selected at random or it's selected on a random subset of the features. Ensemble algorithms basically evaluate multiple trees into a forest and average their outputs. The most performing algorithms currently are based on boosting and include AdaBoost, gradient boosting decision trees, or XGBoost. In order to classify the literature, it is important to identify what is the task at hand. That is, what is the nature of the data, what is the goal of the task, if the final model should be deterministic or random, and if the model should be a forest or a tree. On the right-hand side, you can see the most common algorithm found in the literature. We know that the choice of the learning algorithm conditions drastically what needs to be computed and exchanged during the process. For instance, in IG3, which is a greedy algorithm, the parties need to compute the information gain that requires the computation of the entropy function. While in the CART algorithm, the Gini index needs to be evaluated, which is represented by a quadratic function. Now let us look into the collaborative models. The first thing is to understand how the data is partitioned among the different sites or parties in the collaboration. In the literature, we have identified 2 main partitioning. The first one is called horizontal because the feature space remains the same across all the different sites. Only the data points differ. The second partitioning is the vertical one, where all the data points remain the same, only the features differ. As previously mentioned, depending on the learning algorithm, the partitioning can induce different exchange of data. For instance, in ID3, one needs to compute the count of data point for every feature, for every value of such feature. In the vertical partitioning, this is not an issue because every site has access to all the data points for a specific feature. However, in the horizontal partitioning, collaboration is required to evaluate the global count for all the data points in the dataset. The second part of the collaborative model is to identify which entity is present in the collaboration. We denote by party the entity that owns some local data and wishes to take part in the collaborative learning. The miner is the entity responsible to actually compute the learning process, whilst the aggregator is here to aggregate intermediate values or raw data from multiple local parties. We denote just briefly the querier, which is an entity that queries for the final model for prediction. In the non-collaborative model, the local party can communicate with the miner to establish a model that will be queried by the querier. The first collaborative model we identify is the centralized one, where all the parties send their raw data to a miner who would then compute the learning process as if the data was never partitioned. A similar though different approach is the offloading one, where the local data is sent to an aggregator that creates a centralized dataset, and a different entity mines on the dataset that has been offloaded. In the aggregator-based scenario, each party keeps its local data local, and only intermediate values are exchanged with an aggregator. As previously mentioned, this can be the feature counts in the ID3 algorithm, and the aggregator is here to compute the overall count for a specific feature value. The final collaborative model is the fully distributed scenario in the two-party or multi-party setting, where only the entities owning local data can be involved in the process. As mentioned, the collaborative model has a major impact on the learning algorithm and what information needs protection. Before looking into the protection mechanisms, let's look into the threat models. In order to protect the privacy of the data, the intermediate values, and the resulting models, we need to establish what are the capabilities of the adversary or adversaries in the collaborative model. Indeed, each entity in the collaboration can have an alternate motive to cheat or disrupt the learning process. In the literature, we distinguish three major behaviors: the honest one, the semi-honest one, and the malicious one. Most of the surveyed works consider the semi-honest scenario, as they report the malicious setting introduces massive constraints that can lead to communication and computation overhead. As an example, the centralized collaborative model can either be in the honest scenario, where the data is sent in the clear to the miner, or can be considered in the semi-honest scenario, where the data is protected prior to be offloaded. Now let us look into the protection mechanism. From the literature, we identify four main different approaches to privacy-enhancing technologies. Of course, hybrid solutions can also combine multiple of them. The first one is based on perturbation and randomization. It basically creates a surrogate dataset by perturbing the original one. Considered in the central and offloading models, the parties would perturb the dataset by either adding noise or doing discretization, or swapping the dataset with a new one following the same statistical distribution. However, this can come at some accuracy losses, as the learning is eventually done on an approximate dataset, which might not be acceptable in some cases. Additionally, some attacks have been shown to show vulnerability of such approaches, specifically in the case of noise addition. But these approaches lack formal privacy definitions and were introduced before the notion of differential privacy. Differentially private mechanisms can indeed be employed to protect different information. It can be considered in numerous collaborative models, such as the centralized, the aggregator-based, or even the fully distributed one. 4 aspects need to be considered though. That is, who adds the noise and at which training stage, and what is the privacy budget and the overall noise magnitude that is added to the information. In the literature we observe, privacy budget can deplete quite rapidly. Thus, several tricks have been employed to reduce this by either relaxing the learning algorithm, by, for instance, opting for the Gini index instead of the information gain, as we have seen, resulting in the use of a quadratic function instead of a logarithm, or even considering a completely random split. Other tricks involve, for instance, learning on independent subset of the data, but one might lose the benefit of collaborative learning, or use a differentially private generative adversarial network to create surrogate datasets. Another approach is to locally train a tree under differentially private guarantees, and then share this tree to the next party who can use it to bootstrap its local learning. However, the issue is that there is a huge trade-off between privacy and utility, as the more noise is added, the more privacy is obtained, but the less accurate the resulting model can be. Cryptographic approaches are mainly based on secure multi-party computation and homomorphic encryption. In SNC, the best performing solutions are using the famous SPIT framework to enable sharing of the secret and then the computation in an MPC manner. It can enable almost exact learning to the approximation of the nonlinear functions and can cope with numerous collaborative models, such as the centralized one, the aggregator-based model, and the fully distributed one. However, to keep efficiency, several solutions also replace the gain function by a more amenable one, switching the logarithmic evaluation in information gain by the Gini index and the quadratic function. However, it's harder to tolerate unavailability, that is, when one of the party might be offline during the training. Additionally, communication overhead is also non-negligible, and trust assumptions can be restrictive, for instance, in a trusted preprocessing scenario. Homomorphic encryption can enable computation to be executed directly in the ciphertext and can lower the communication overhead induced by SNC solutions. Similarly, they can adapt the learning algorithm to a more amenable one with the Gini index or even with completely random splits. However, the drawback of homomorphic encryption is that it's hard to compute comparison under encryption. Thus, in numerous works, the intermediate values are decrypted to identify the base gain. Other solution can be leader-based, that is, with different entities having different role in the learning, and specifically one for encryption, one for decryption, and one for blind text. Most of the solutions are relying on the Payet crypto system or its threshold variant. The main drawback of homomorphic encryption, however, is that it's quite difficult to evaluate nonlinear functions and to evaluate the comparisons. Another approach is based on hardware solutions. In this scenario, each party has an enclave on which the data can be offloaded, and the secure enclave is responsible for storage and computation of this sensitive data. Remote attestation protocols can cryptographically verify that the software has been loaded correctly. However, this relies on different trust assumptions, as one needs to trust the manufacturer of the secure enclave. Additionally, it might be susceptible to side-channel attacks and needs to be coupled with additional countermeasures. The most promising approaches, however, are based on hybrid solutions. For instance, by combining SMC and randomization, the amount of communication can be reduced and obtaining better accuracy than simple randomization. Numerous cryptographic approaches can also be combined to obtain communication efficiency from homomorphic encryption and using the SMC for nonlinear functions such as comparisons. DP can also be combined with cryptography to reduce the amount of privacy budget required at each step. And finally, as mentioned, secure hardware and cryptography can be combined to prevent side-channel attacks. Now let us briefly introduce our leakage analysis framework. As previously mentioned, in the collaborative learning, several information can be shared during the process that are not always protected. Thus, we design a framework to analyze which kind of information is leaked and at which step of the learning process. It can be, for instance, raw data, intermediate values, or model parameters. Our framework identifies what kind of information is leaked and who can potentially take advantage of such leakage. For instance, in the centralized model with DP mechanism as protection, raw data is inherently leaked to the miner as it is the one responsible to add the DP protection. But we know that also improper privacy-enhancing technologies, such as perturbation in the centralized collaborative model, could lead to raw data leakage, as we have seen. Intermediate values can be used to obtain global information about the local dataset, such as class count, for instance, or they could potentially be used to, in combination with the final model, to do membership or inference attacks. We note that intermediate values can be local, pertaining to only one specific entity, or global. Overall, we identify that very few works keep the final model private, and even fewer works prevent the leakage of intermediate values with appropriate privacy-enhancing technologies. Overall, we identify 4 main open challenges. The first one is to study the leakage in tree-based models by investigating privacy attacks from intermediate values and quantify the risk of such leakage. The second one is how to cope with malicious setting. Porting the field to the any-trust or even fully malicious setting remains a challenge, but recent advances in verifiable computation and cryptography are promising. Byzantine tolerance is also an interesting avenue for future works. The third challenge is how to provide end-to-end protection of the learning process, protecting the input, the intermediate values, and the final model at the same time. The last challenge is how to cope with resilience and fault tolerance. That is, what is happening when a party wishes to leave the federation, or if a party is unavailable during some time in the learning process. These points are inherent to the learning process collaboratively, and very few works have considered it for the tree-based models. In this work, we have systematized the literature on privacy-preserving collaborative tree-based model learning. We have identified that the collaboration introduces several challenges that can be coped by modifying the way the learning is executed or adding new entities. Additionally, while numerous privacy-enhancing technologies have been employed and deployed, hybrid solutions are the most promising. We have also provided a leakage identification framework to help designers and researchers categorize the literature and reason about what information is exchanged to whom during the learning. Thank you for your attention, and I'll be happy to take any questions.